Hi everyone. As we look into image formation, I just want to review how we see objects. So objects emit light rays that will then enter our eye, and the eye acts as a lens to form an image on the back of the eye. The brain will interpret that signal up from the back of the eye and trace back those light rays to produce a picture of what we're seeing, and of course this is instantaneous. So mirrors essentially work in the same way. When we see something that's in a mirror, our eye is interpreting that light ray that enters our eyes to have moved in a straight line and tracing it back and forming an image. So let's consider a plane mirror. It's this vertical surface here, and I've drawn an object in front of the mirror here. We know that the light rays from the object will go in all directions. So we'll see in this chapter that we can use just a few light rays in order to locate an image. So I've drawn three here, one that goes straight perpendicular to the mirror, and then two light rays that follow the law of reflection. Of course, they all follow the law of reflection for these plane mirrors. So if one of these rays were to enter our eye, we would see this as if it came from a straight line, as if it originated from behind the mirror. So in order to locate the image, we need to trace back those reflected rays behind the mirror. And when we do that, we see that they cross at a point. This is the image point. So this is the point that the reflected rays appear to originate from behind the mirror. And this is a virtual image. So there's two main characteristics of a virtual image. One is that real light rays do not cross at the image point. And the second is that if we were to take a screen and hold it up behind the mirror at this point, we would not see an image on the screen. And we know that if you think about doing that with a mirror that you have in your house, there would be no image behind the mirror, yet when we look into the mirror, it does appear as if the image is behind the mirror. Okay, I just want to mention two important characteristics about images formed in a plane mirror. The first is that the object distance DO equals the image distance DI. So if the object is placed at a location of DO in front of the mirror, the image will form at a distance of DI behind the mirror, and those two are equal. The second, and we know this too, is that the image height equals the object height. So we see objects at the exact same size, their actual size, when we look into a flat plane mirror. This means that the mirror has a magnification of 1. So after this section, we're going to look at other types of mirrors that produce images with different characteristics, but this is just for a plane mirror. Okay, I just want to go over quickly how to find an image that's formed in a plane mirror. Consider each point separately. So if we want to find where the top of this object is formed in the mirror, this is my object here, this arrow, I'm going to draw two rays from a single point, so from the top of that object to the mirror to reflect at the mirror. Any two rays, but when they hit the mirror, they need to follow the law of reflection. So one can be this perpendicular ray here, and then the second one I've drawn so that it intersects here, but any location is fine as long as you approximate that law of reflection. Could measure if you're not sure, but I'm just doing a sketch here. And then extrapolate the reflected ray. So this is the reflected ray. I'm going to extrapolate that back to find where the image is formed. So where those two rays cross, that's the top of this image arrow. It's different if you have an eye or a person who's looking into the mirror and you want to see the object in the mirror. Then you would need to draw the two rays to enter the eye, and I'll do that in the examples. A woman 1.6 meters tall stands in front of a vertical plane mirror. What is the minimum height of the mirror, and how high must its lower edge be off the floor for her to see her entire body filling the mirror? Assume her eyes are 0.1 meters below the top of her head. It's really the eye location that we need, and we also need the length of the object that we want to see in the mirror. So I've drawn this rough sketch here. This is the person. I think it helps to make the head really big just so we can see where the eyes are. And then this is the wall, or where the vertical line where the mirror will be placed. Okay, so for this woman to see her entire body, she needs to have a ray from the top of her head and from her feet hit the mirror and then reflect into her eyes. So let's look at the feet. I've drawn a ray that goes from her feet to the mirror, and then it reflects into her eyes. And then I've drawn another ray that goes from the top of her head, it hits the mirror, and then it reflects into her eyes as well. And with this positioning, she'll be able to see her head and her feet. So we'll need the mirror to be here. This is our mirror. I mean, it can be longer than this, right? We just need at minimum to have the ray from the top of her head hit the mirror and from the bottom of her head hit the mirror. So let's figure out how long it is and how high it has to be off the ground. Let's first look at this ray. We know it follows the law of reflection here. These angles are equal. And this side of the triangle is equal. I could extend that, but it's just this distance from where she's standing to the mirror is this side of the triangle. So if we have all the angles equal, which we would because this is a right angle, the floor is horizontal, and then so this angle must be the same. All the angles are the same and one side is the same. This means all sides are the same. So we have to have this intersect at the midpoint. And you can kind of just see that because we know that if this angle is equal, in order for that to be true, it must hit the midpoint here. So the midpoint is from her eyes, which are at 1.5 meters from the ground to the ground. So we know that this length here is 1.5 over 2, which is 0.75 meters. So it must be at least not less than 0.7, or how do I say this? So it has to be at a minimum 0.75 meters to the ground. It can be closer as long as it's longer, but this is the minimum positioning. So, okay, mirror must be 0.75 meters from the floor, or closer is fine too. Okay, but if that's its minimum position, now we can find the length, basically by using the same logic. So the other half of our 0.75 meters is right here. And then we want to find this little extra height that's needed to see the eyes, or for her eyes to see the top of the head. So by the same logic, in that portion up here, we have to have 0.1 meters over 2 in order for this ray to follow the law of reflection right in there. So we want the other half of this distance there, which is 0.05 meters. So at this height, it must be, our total length is 0.75 meters plus 0.05 meters, which is 0.8 meters long. And notice that this is actually a general result. So in order to see the full length of your body in the mirror, you need a mirror that's at least half your height. And in order to see any object in the mirror, you need a mirror that's half the height of the object. The positioning does matter, of course, which we checked in the first place. So this is a bit counterintuitive, but it actually doesn't depend at all on the distance to the mirror. We didn't use that number in our calculation. You can check that at home. So try moving back, moving away, and moving closer to a mirror that's on the wall. You'll see that you actually always see the same amount of your body in that mirror. Example 2, two plane mirrors form a right angle. A small object is placed between the mirrors. How many images do you see? Okay, I've tried to draw this here. So here's mirror 1 and this is mirror 2 at a right angle, and this is the object. Now, to find the image, we need two reflected rays. I've just drawn one because we know that the image will be formed in one mirror from the object will be a distance equal to the object distance behind the mirror. So we know there's going to be at least two images, one of the object in mirror 1 and one of the object in mirror 2. Now there will be a third image. The third image is produced by the image in mirror 1 in object 2, or you can think of it as the image of the image in mirror 2 in mirror 1. And to find it, we can trace the rays. So let's reflect a ray from the object that hits the mirror 1, reflects off mirror 2, and then reflects according to the law of reflection. If we extend that reflected ray, mine's a little bit rough here, it's not, I didn't use a protractor, but it will go back behind the intersection of these two mirrors. And I can draw one more ray here so we can see the image. It's this one. It hits the mirror, it reflects, and then reflects again. And we extend that reflected ray to find the image behind the two mirrors. And you could draw more rays as long as they reflect between the two mirrors. They should all the extrapolated rays should end up meeting at this point. So in total, we get 3 images. Okay, to summarize, let's go over 5 main characteristics of images formed by a plane mirror. So first, we know that the image is virtual. Second, it's upright, so we see it in the same orientation as the object. And third, it's unmagnified, again, HI equals HO, so it's the same size as the original object. Then I haven't talked about these two yet. It's left-right reversed and front-back reversed. So left-right reversed really comes from the law of reflection. These light rays are reflecting, and it's the reflected ray that enters our eye. And if you were to draw that on a scale on a width of the object, you would see that that means that the reflected rays are crossing. So to us, it looks like the orientation has switched. Then front-back reverse, this is because the light rays from the front of the object are what are hitting the mirror and then entering our eyes. So that is what we see, the front of the object or the side that's facing the mirror. Okay, in the next section, we'll look at spherical mirrors.